My name is Vikram Rao. I'm an undergraduate at Cornell, and together with Kailash Patil, we worked on distributional features and clustering for Ngrams. So in the vein of previous presentations, our nail is clustering phrases in the Google Ngrams based on distributional features. So why would we want to do something like this? Well, clusters allow us to make generalizations about something that's unseen using something that we have seen. So for example, we know that Honda Accord is a car. So based on cluster membership, we assume that maybe Nissan Maxima is also a car. So you see on the right here, these are typical members of the cluster, which actually does contain Honda Accord. This is the actual cluster that we got from the Google Ngram. So you can see that it clearly contains a list of car models. So we could also ask, is Peace Accord a car too? So we look at the cluster members for Peace Accord and Honda Accord. So Peace Accord, clearly, as it should be, is not in the car cluster. Instead, it's with the cluster consisting of other agreements. Secrecy agreement, memorandum agreement, et cetera, et cetera. Honda Accord, of course, is with the other cars. So how did these phrases end up in their respective clusters? Well, our answer was distributional features. So you can see that the top features for the Peace Accord cluster are things like signed appearing on the left, signing appearing on the left, between occurring on the right. These are typical words that you'd expect to find in the context of a phrase like Peace Accord or any similar one. On the other hand, the features for the Honda Accord cluster are things that you would expect to surround a phrase which is a car, like obviously car, recalls, engine, used, things like that. So this is a good way to separate things into clusters using distributional features. Now, what we want to do is make clusters of phrases. The reason for this is that clustering billions of Ngrams would be essentially impossible. So we've reduced it to approximately 10 million phrases. And to choose phrases, we use a very simple idea that Ngrams that have a low entropy of context are not phrases. So take, for example, the trigram degree in computer. Now that has a count in the data of about 52,000. Now take the foregram degree in computer science. That has a count of about 40,000. That means that 76% of the time we see degree in computer, it's followed by the word science. This would probably lead us to believe the degree in computer by itself is not a very good phrase. Now after degree in computer science, if there was no preference for one select word, then we could probably conclude that degree in computer science is a decent phrase. So what we do to identify the phrases in practice is to use heuristics that approximate choosing Ngrams with a high entropy of context. So we want to look at things like minimum number of unique features, features on either side, minimum sum of feature counts. We also want to ensure a minimum stop word percentage for the phrase, because we kind of use the idea that atomic phrases can be glued together by stop words. So we want to have a minimum number to get an idea that it's a phrase. We also don't want to start a phrase with a stop word. We also apply some very simple filters on the POS tags of the Ngram since the data was tagged. And this just eliminates some very blatant non-phrases. We don't want to begin or end in conjunction or symbol. We don't want to have period or comma in the middle of the phrase. We don't want to end in a preposition or determiner. And there are a couple other rules like that, but they're very simple, very easy to filter out the phrases, the non-phrases. So now we look at extracting the distributional features. So we're interested in foregrams, trigrams, bigrams, and unigrams. And the higher order Ngrams will give the distributional features for the lower order Ngrams. And this is greatly facilitated by having the rotated data that De Kong has already introduced. So that makes it very easy to, in one pass, extract the features while simultaneously identifying the phrases. So in one pass, we can do both of these things and be as efficient as possible, given the large amount of data that we have. So here's an example of how we would go through the data and collect the feature counts. So we have degree in engineering, which appears about 32,000 times. So we start building the feature count vector. So that greater than less than symbol, as De Kong mentioned, is sort of the end of the Ngram. So after that, everything is mirrored. So PhD actually appears on the left. So there's PhD degree in engineering, accredited degree in engineering, and so on. So we see that occurs 110 times. PhD occurs 110 times to the left of degree in engineering. So we add that as a feature. And now accredited occurs 21 times to the left of degree in engineering. So we add that, and so on and so forth. And then with one pass, we can build this count, the counts of the features, distributional features for the phrase degree in engineering. So, but what we want to do is we don't want the raw counts, but we'd rather have the mutual information between a feature and the n-gram. So for example, so that's given by this formula here. The mutual information of W, the n-gram, the phrase rather, with the feature f is given by the log of the joint probability of W comma f over P of W, P of f. And that can also be written as a log of P of f given W over P of f. So P of f given W is simply obtained from the feature vector. And P of f is simply the global count of the, obtained from the global counts of the features, which we calculate in an intermediate stage. So what we then do is convert the counts in the feature vector to mutual information. So right now we have the counts here for degree in engineering. Those simply become mutual information values. And so to do all this feature extraction, we use Hadoop. So without that, it would have been impossible to even cluster the 10 million phrases. And to do the complete feature extraction on the whole data takes only about 1 hour. We use the Google IBM cluster, and when it's up and running, it only takes 1 hour. So now we have these mutual information to do vectors with which we can do k-means clustering. And now I'll turn it over to Kailash.
Hi, I'm Kailash. I'm a graduate student at JHU. I'll be talking about k-means clustering and one of the applications that we actually dealt with. The reason we chose k-means clustering is we have enormous amounts of data and we need a really efficient, computationally efficient algorithm. And it's also unsupervised, and the thing is we needed it to be extremely parallelizable, and k-means is supposedly embarrassingly parallelizable, and it was. And so we just did 50 iterations, and we chose 1,000 random data points as the starting point for the k-means. I'm not going, and we used, as a distance metric, we used cosine similarity, which is just the cosine of the angle between the two feature vectors, and this is the formula for that. I'm not going through the animation for k-means clustering, and I'm assuming everybody knows that. And this is a sample cluster which we got from k-means clustering, and yeah, so this is a cluster of Indian names, and as you can expect, the features are common suffixes and prefixes of Indian names like Singh or Kumar or Shri. So one of the applications that we dealt with was noun-compound coordination disambiguation. So we chose we chose patterns of phrases which had this pattern, that is nouns, CC is a conjunction, and noun. So this is a 5-gram, and an example is US Consumer or Business Magazine. And the ambiguity here is that the consumer or business can go together, or consumer and business can be put in two separate brackets. This is the main difference. That is, the second and the third word, either they're grouped together or they're split apart. So type 1 is where they're put together, and type 2 is they're put apart. And we use the fact that the constituents of this 5-gram, some of the constituents are similar to others, and we try to use this to resolve the ambiguity. Before we go into the actual steps of how we did that, we have to introduce the notion of phrase similarity. So what we did was we took a phrase like this, US Consumer, and we just got the top clusters for that phrase. And the top cluster was cluster 470, and these three are the top elements in that cluster. And the similarity to that cluster was 0.18. And so on, the second best cluster for that was 458, and so on. So we constructed a feature vector for this phrase which goes like that, 470, and the similarity to that is 0.18, and 458 and 0.15, and so on. So once we have the feature for this, we also get the features for other constituents in the 5-gram. And once we have the features for these two, again we use a cosine similarity between these two feature vectors to calculate the similarity between phrases. And this is what we call phrase similarity. And once we have this phrase similarity, we calculated phrase similarities for different constituents. So AB and AC, we calculated that. We calculated for BD, CD, and AB, CD, and so on. So AB and AC would tell you that US consumer is similar to US business. So which means that there's a probability of consumer and business being bracketed together. So that would be type 1. Whereas if AB and CD were more similar, then we would bracket US consumer separate and business magazine separate, and that would be type 2. So we use this table, and there's this backoff thing we used. So what this backoff is, if we do not have some of these constituent phrases in the clusters, we just use this similarity between B and C and B and D. And this is an unsupervised method, so we just use the max. So we just use this metric to decide the type of bracketing.
Excuse me, what does type 1 mean versus type 2?
Type 1 means that B and C are bracketed together. So type 1 is the second word and the third word are bracketed together.
Okay.
Type 2 is they are separated. And as a sanity check, we just wanted to check if clusters are actually helping us. So what we did was we took the counts from the Ngrams. So we calculated the mutual information between B and C and B and D using only the counts. So here n of B con C is the count for that phrase B and C, and so on. So if that is high, it would imply that it's type 1, and if the mutual information between B and D is high, then it would mean that it's type 2. So using this, the data was got from Pentree Bank, and we extracted all the phrases for that particular pattern. We got 602 unique phrases, and using no backoff, we got a result of 75.7 accuracy %, and using only the backoff, that is B and C and B and D, we got 73, like 72.9, and using both, we got 82. So this shows that clusters indeed help us, and the count-based method we used, that gave us 74.3. So it's a significant gain over the count-based method.
3 and 4?
So what do
You
you?
only considered types 1 and 2.
Yeah. So that's the only two classes that we consider.
Well, so you threw all the others out?
No, in any class where B and C are grouped together, that is, we put them in type 1. There are no other.
Regardless of where A goes.
Yeah.
Yeah, because
So if there's a huge
real conjunction ambiguity is really between like whether the second and the fourth words are conjoined, or the second and the fifth word are conjoined. Like, say, so like U.S. Consumer and business, like if you group them together, and then magazine, like once you group consumer and business together, like it becomes like a 3-component compound noun. And there are still further ambiguity, but that ambiguity is not related to any sort of similarity. Like it's really related to like what like this three-word. Like if you have 3-word noun, like then there's like a 2-way ambiguity. But we're not resolving that ambiguity. We're resolving the ambiguity just regarding the conjunction. So there are only 2 choices.
So all the types of bracketing which in fact bracket B and C together.
Okay, so you basically, the bracket, you simplify the bracket.
Yeah.
You said type 1 and type 2.
Yeah.
So we successfully extracted features. We extracted phrases. Sorry, that should have been phrases. So we successfully extracted phrases, around 10 million phrases, and we were able to cluster them, and we also demonstrated the benefits of these clusters towards this particular example. And there is more potential for clusters in different applications like compound noun bracketing or named entity extraction, as Sushant was saying. We also have a demo, and Vikram will explain more about the demo.
Okay. So we'll try to make this short because we're pressed for time. So what you can do in the first demo, the clusters demonstration, is you can enter a phrase, so it'll go and search through the clusters for the top members that phrase belongs to. So the clusters to which the similarity between the phrase and that cluster centroid is the highest. So for example, if we want to look for degree in computer science. Okay, degree in computer science. Okay, and then say we want to see the top 5 clusters that degree in computer science occurs in. And say we want to see 10 phrases for each one. And then we can also see the top features for each cluster centroid. So why did those elements come into that cluster, basically. So say we want to see top 10 features. So we can hit submit. So now we see that the top, the closest cluster to degree in computer science is 925. And you can see the top phrases in this cluster. So we see degree in philosophy, degree in mathematics, degrees in business administration. So this sort of thing would be kind of useful to what Sushant talked about. And you can see the top features for this cluster. As you would expect, bachelor, masters on the left, undergraduate, things like that are very indicative that we're looking for degrees. And then there's some lower clusters which clearly aren't as relevant, depending on what you're looking for. So the second demonstration is just. We didn't want to do that because of time issues. But okay.
WMD, one word.
Okay.
Program related activities.
Yeah.
Maybe just WMD program.
Yeah.
Okay.
5-year strategic plan is that.
What about
Final action
What
plan,
about
that's it.
final action?
Doctor Strangelove.
I mean, it's not computer filter.
I'm just thinking that because it was Google data, maybe there will be lots of examples.
Yeah, we should run this as an SAP.
Okay.
So if you want to, second one, okay, yeah. So the second demonstration is just finding the similarity between 2 phrases, and this is done using the same feature vector that Kailash talked about earlier, where we make construct a feature vector based on cluster memberships, and we do the cosine similarity between those 2. So for example, we can look at LaGuardia Airport, and then we can look at JFK Airport. So those have a very high similarity between the 2. We can
Just take a picture.
so much more. Yeah. So if you want to play with this some more, you're welcome to the.
Is it because of the airport, the token airport import the phrases that it gives high similarity? What if we had VWI and JFK? Would it give high similarity because both are airports?
Well, we can try, but JFK may show up in many other things.
Okay, VWI and ID maybe.
Here.
That is unambiguous.
Like you said, GST gets used for other.
Yeah. So if you want to play with this, just go to this URL and you can play around. Thank you.
Okay, so I'm going to talk about some tools. The input, say, let's imagine I have just a bunch of flat files. I've got a bunch of different examples I'll show you. I split the fat file, the flat files into what I'll call pages, say 2 gigabyte chunks, and then I can assume that I can do random access within the chunks, and I build indexes for each of the chunks. I'm going to support a bunch of different types of match types. Exact match, Emily talked about that. Starts with, contains. And we've got various different filters like return everything that matches, or just the best, or just the longest. I'll talk a little bit about a part-of-speech application that Emily talked about several weeks ago. So this is an older version of the clustering file that we just heard about, in which there are about 1,000 classes, I think exactly 1,000 classes, and 7 million phrases. And there aren't any glosses, but I added some just to give some sense of what I think they're about. And there seems to be some method to the madness, and we saw in the earlier demo that there's something to this clustering. And I wanted to provide some indexing to it. So for example, here you could look for all the phrases that start with some substring or contain some substring. And in this case, many of them are in this class 131, but not all of them. And here's where I get some better sense of that the degree in phrases are overwhelmingly in class 131, but there's some exceptions. Then I show some examples of what each of those classes look like. Then the next thing you can do, and I've sort of been fascinated with what can you do with all substrings. So could you say, compute for all substrings in the language, what are the classes that they're sort of significantly associated with? And here we've done something like that. And there seems to be some pattern where things that can, sort of have that substring in it are overwhelmingly in 131. And these guys are overwhelmingly in 472. You could probably build a mapping from all substrings to these classes. So just to sort of summarize where we are, we have these input files, which are basically tuples. The keys I've been talking about, say, are the Ngrams. The values would be the parts of speech. The score would be counts. In some other cases, we have different things. Support different kind of lookup functions. And I'll talk a little bit about different filters. But before I go that, let me show you some data that I just got yesterday from Switchboard. And this is a speech application where each of these P something or others are the output of some clustering from BBN. So this is just a big string. Each line is a turn in Switchboard, and it's labeled by some method who knows exactly what it does. And what I'm trying to highlight in some of the long boxes, and what this is doing, is looking for relatively long repeated substrings that are in different utterances. And you can see that the labels at the end, the SW, whatever, those are pointers into the Switchboard database so we could get the waveform files and whatever. And the boxes here, I want to highlight that there's an interesting thing about both the width of the box and the height of the box. The width of the box is how long the repeated substring is, and the height of the box is how many times I found it. And those are both important.
It's reasonable to assume that each of these units are about the same.
Well,
To believe that the width of the box.
there's certainly, the lengths are not, they wouldn't make sense in terms of milliseconds. But I think that, I don't think that when you're comparing two speech utterances, you want to compare them in terms of milliseconds either. The thing is, I think that long repeated substrings in this space are probably indicative of something important and meaningful.
The reason I'm asking, for example, is that let's say 325, 321
Yeah.
were fairly long segments.
Yeah.
Each of them is I'm not saying that every instance of
But again, I disagree with the assumption that length in terms of milliseconds makes sense. I think length in terms of TF-IDF would make more sense.
No, what I'm saying is you don't need to have an exact sequence match. If there was a third instance,
Oh.
325, 312,
All right.
321, and 312.
So look, that we often get, I think, distracted by that. If I have enough speech and I'm finding the patterns are repeated, then you can find the easy, obvious pattern. Then you want to find variants of that.
I see.
All right?
precision
So,
is different.
yeah. So, I mean, like people let me not go down that route, but I think people, for example, in search on the web, we could get very distracted by, well, people don't type, don't spell their queries correctly. Yes, but most people spell them correctly. So you look at what most people do, and then you find the variance. Anyway, an interesting little factoid is that these boxes actually form an interesting structure. They actually form a tree, so that there are many ways to draw boxes around these things. Some longer, some taller, but they actually form a tree, and it's possible then, because of this tree structure, to find all the substrings in a feasible amount of time. It's not a huge job. Yeah.
So just to be clear, this is an already sorted suffix array that we're looking at.
Yeah. In order to get all of switchboard onto one slide, obviously switchboard goes on for hours. Right. Yeah. So what you're looking at here, another way of putting it for this audience is that it's like a concordance or keyword in context. So this thing is all sorted alphabetically by the lines, and because of that, the things that are repeated are near each other in the slide, and so the boxes can easily capture what we're after. Let's go back to our Ngram data structures. In here in the yellow, I'm sort of highlighting looking queries that are over the Ngrams stuff. And again, here I didn't tokenize or anything, so the query was he drove T, and you can get all these matches. He drove T. So I actually do not tokenize. That's where it is, at the top right, yes. Okay. Yeah, I guess I do have a laser pointer, but hey. Now in the next one here, I've added to this an optional argument of 10, which now means don't find all the matches, but find the best ones, and the best by the score, and in this case the score of those counts in yellow. So when I put in the same query, he drove T, then he drove the comes to the top, and it returns a list of only 10 answers as opposed to many more. Now, the way you can do k-best is an interesting little variation on the standard suffix array. The standard suffix array is where I take a string, say imagine I have the corpus to be or not to be, and I would then label it with those positions, and then a standard suffix array just sorts the positions by alphabetical order, as in here. And then you can do many of the queries that we described, but it's not good for k-best. It finds all matches, but not the best ones. And finding the best ones is actually harder than finding all of them. Right? So what we do is, for a k-best suffix array, is that we have two orders. One is alphabetical order, and the other is by the score order. And you can interleave them. So at the top level of the tree, I sort by one order. And then on each half, I sort by the other order. And then within each half of those, I sort by the one order. And you alternate going down the tree. And this way, in sublinear time, I can find all the best matches as opposed to all matches. So the data structure is just another permutation of the same array, but it's permuted in a different way. Then I also mentioned longest match, which is another variation on the same idea. So here, you input the string he drove to work, and I'm going to find that was the original input. Actually, I think I've deleted in this slide the thing that it matched, but there were some parts of speech sequence that it came to. He drove to the something or other. And so I matched against something else because I didn't have exactly that in the corpus, in the Ngram corpus. And then here I took this piece of it and entered it again, and then I have a match. And here I've got a match with a couple of possible, work is either a noun or a verb, with different counts, and then work is either a noun or a verb, and so on. So you put in the one input and you get all of this data structure out.
I don't
Yeah.
understand how you're sorting by counts, because...
Oh, this is not sorted by...
No, I'm talking about the previous slide.
Oh, the previous slide.
Because...
Oops, how do I go backwards? Here. Yeah.
Surely in the suffix array, like each element is each individual position, and that it doesn't really have a string length associated. Well, you have to know the string length to work out the count.
No. The counts are the counts are completely, they're different from lengths. So I'm assuming that this doesn't have in there, but I'm assuming there's another object someplace else. I didn't put it down here that tells you about the score feature. So I had as input 3 things. I had the strings, I had values, and I had scores. And what I'm saying is that this thing is sorting alphabetically by the strings and also by the scores.
Okay. Wait, so you said it's sublinear at time. How sublinear?
The worst case is square root as opposed to log n.
And linear memory.
It's the same memory, yeah.
Okay.
But the worst case doesn't actually typically come up. I can explain.
So log n or something.
Well, there would be an n log n solution for all matches, and for the best matches, I know how to do it in worst case of square root. And the worst case is when there are no matches. So this has been shown before, which is that previous thing showed a lattice of different, here we had different parts of speech for these different, for each word I show these different part of speech possibilities. And the lattice, this can be treated as a lattice, and what you're trying to do for a part of speech tagger is to find the best path through this lattice. And I used a dynamic programming solution. And unfortunately what that's showing in the red is that what we end up concluding with that in this case is that work is incorrectly tagged as a verb, which I think the evidence in the tag data set we had would lead you to that mistake. So just to summarize where we are, we input a bunch of flat files. I've given a bunch of different examples of it. And then you can have fairly general type of matching, fairly general type of filtering, and I think this could be used for a bunch of different applications. So thank you.
Hi everyone, my name is Kapil Dalwani and I'm a master's student at the Johns Hopkins University. I've been working with Professor Satoshi for the past few weeks to build an Ngram search engine. So currently the search engine works only on the Wikipedia data, but you can extend it to any data source of your choice. So working on the same theme of hammer and nail, our task is to build a hammer which is like a multifunctional fast search engine. So the search engine, so the input to the search engine can be not only tokens, but it can be part of speech, name, entity, and chunk information. And the output, in terms of output, you can not only get the frequency count, but we can link you to the direct text of the Wikipedia. So here are the few salient features of the search engine. Our search engine supports searching of up to 7 grams. It also supports some wildcard queries. And in terms of input, you can not only provide the token information, you can provide part of speech, chunk, name, entity, and there are some. You can use the combination of all these 4 categories. And you can also provide the union and the intersection of part of speech and name entity. In terms of output, we not only output the frequency count, but we also output the part of speech and name entity information related to the Ngram. And finally, if you want to link to the direct source of the text, we can just link you to the source of the Wikipedia data. And the results are shown in the order of decreasing frequency. So the Ngrams which are frequent occur at the top, while the Ngrams which don't occur at the bottom. And the key part of the search engine is that we can ship all the index data into a 500 GB USB disk, which can work on a single PCU on a Linux-based platform, and the memory requirement is 400 MB. Our plan in future work is to decrease the memory requirement of the Ngram search engine. Okay, so I'll start with the demo to find some interesting queries. Okay. Oops. Maybe I'll start with this. So let's see, let's know what people usually love. Okay. So people, so these are few of the answers. Now suppose I want to know whether what people love in terms of person, so I can just specify the name entity in terms of person, and you can say that people love Jesus, people love Mark Twain, whatever. Like, and suppose I want to know about the location, like where people usually tend to go. So you can specify the location and say, okay, people of America, people of France, and all. So you can get some useful queries out of it. So one of the queries would be like, somebody is so in this query you can get the not only the dates and the places where people get usually married. It's not usually this slow, but maybe because of the internet, it's taking time. Okay.
But isn't it querying from the
Okay, I can try that. Let me try this one. Okay. Yeah. So as you have noticed, I specified the CD in the part of speech, so you can come to know that what all time people got married. I can change it. I can remove the CD option. And there you go. So you not only get the time, but you also get the place where people usually got married. Okay. Any queries like people want to search for? Yeah.
So I noticed something that looked like an error, just curious where it came from. When you had person as the word preceding was married, usually that worked, but once it got woman who.
Once it got?
Woman who was married in, why did that match person?
I think the data is tagged using the Stanford tagger. So,
Yeah, so there's just a
maybe it's
identity tagger.
Yeah, maybe, yeah.
Maybe person doesn't just mean a person's name, but also who and woman are kind of personish. I don't know.
No.
They're not named entities.
I can imagine the target thinking that woman who is a name.
Like Thaho.
Let's see what this returns in. Okay, yeah. So people got killed in road accident, people get killed in a railway accident. And there's something which I found interesting was people got killed in a photography accident.
Can star be null?
What's that?
Can star be null? I mean, when it's a
zero more methods?
No.
you can't skip over it. In other words, it can't be compressed.
Oh,
You know,
Star
star is like
Star is like a wild card.
It's more like question
so
mark.
there's got to be something there.
Yeah.
Yeah.
Is that too difficult to change?
So
So it could be blank as well?
Change so that it means zero.
It means both zero or something.
0 or more.
Yes.
But zero means you just search I killed in the accident.
Yeah, of course you can do it, but this way you don't have to list
Yeah.
everything.
So, yeah. Okay, so this was something which I found pretty strange, like somebody got killed in a photography accident. So maybe we can just find the actual text of what does it happen? So
Those are the most dangerous.
So yeah, so there are 4 columns. The first column is the title of the Wikipedia page, and the second and the fourth column is the keyword in context, which is the left and the right context of the Ngram search. So like this is like from a famous movie, I guess, which Shane pointed out, King Ralph, in which the whole family got killed in a photography accident.
That's good because it's fictional.
Yeah.
We did a fiction detector.
Okay. Yeah. Oh, okay. Star?
is a famous computational linguist.
Sorry.
Replace famous by star. We like it infamous.
Star. And star.
So, but star is not 0 anymore.
Yeah, well.
Okay. So this web
Neither of
page.
them are famous.
Yeah.
So we're not taking any Australian computational linguists because Australia starts with a vowel. Is there one after A or N?
Not in the tokens, but you can specify in the.
You can put determiner, I guess, yeah. Okay, but there's no way to do disjunctions.
Not in the tokens, but in the part of speech and name entity you can.
I see.
And we plan to like extend it for the
You
tokens. Yes.
can specify the determinant. A or N.
Yeah, but you might want an indefinite determiner of the tag doesn't matter.
Actually, try that because I have a feeling there are lots of American computational linguists.
Change A to BT. DT.
You take out the word.
Remove the A with the stars.
One. There's only one.
Okay. I think I should move on. This web page is available online, so you can play around with it. So this.
Going there, it's
So
authorization.
this is the web page.
Got it, thanks.
So we plan, like this is hosted on the NYU website, and we plan to host it on the JHU. And also, if you want to run it locally, so we can ship the hard drive, and it can work on a single PC working on a Linux platform. So you have few options to play around with it. So now, after doing this, I will just go into the high level detail of how we build the search engine. So we initially downloaded the Wikipedia text from the website, and then we created the suffix array for the whole Wikipedia text, and also we ran some tagger and chunker to get the part of speech and name entity information. So this is where maybe the error lies of the like name entity and part of speech. After doing this step, the next task is to convert the suffix array into the Ngram data, and this is done this is done both for the suffix array and for the Wikipedia. So after this step is performed, our task is to build the search engine. So the easiest way out is to build the inverted index for this Ngram. So suppose when a user specifies a search query, the first task is to get the potential search candidates from these two data, and then after getting some potential candidates, our next task is to do the post filtering, in which we remove all the candidates which do not belong to a particular part of speech or name entity. And finally, we like display the results to the user. So I'll just touch upon each steps in bit detail. So as I already said, the text is first converted into suffix array, which is then converted into the Ngram data. So this is just a sample of one of the Ngrams, say for 3 gram. This is the table we have, and it lists all the possible unique Ngrams we have. So and each Ngram is given a unique ID. So and it's called the forward index. So from this index, we create a inverted index out of it, which is like, this is called the inverted index because it specifies for a given term in what all document it occurs, while the forward index is like in a given document what all terms we have. So building the inverted index out of this is quite easy. You just do the so the key thing to note over is the posting list is not only on the basis of words, but it's also on the basis of positions. So the inverted index is on the basis of word ID A and on the positions of the n-gram. So this is repeated for all the n-grams.
Kapil,
Yep.
when you get the new Wikipedia data, how do you update your index table? Is it incremental?
Not now. Like for that we have to do the entire step again. Okay. So we face few implementation issues with the posting list. This is because some of the highly frequent occurring words like end of speech and the are like comparable to the size of 7 gram. So the 7 gram is like about 1.27 billion words, and the words like the EOS are like 3% of the whole 7 gram data. And some of the words are only occurring once, like words like conspicuous, which is spelled incorrectly, music and all, only have the frequency count of 1. So our task was to divide the entire posting list into 3 different categories. So the first option was to use a bitmap for the words which are highly frequent. So this resulted in a saving of space, because if you try to store these many words in a posting list, the total bits required would be 3.2 billion. But if you try to convert it into a bitmap, the total size required to store EOS in a bitmap is like 1.27 billion. So this was the main reason we used bitmap to save some space. And all the words which lies in the category of less than 1% and frequency count not equal to 1 goes into this category. And some of the words which occur only for frequency count 1 are being encoded into the index data. So after doing all the indexing, the last task is to do the searching algorithm. So suppose a given, suppose the user provides a search query with ABC. So the first task is to get all the posting list for all these 3 queries in an order of increasing frequency. This is usually done to keep the memory requirement at a minimum value. Then the basic task is to get the posting list and do a simple merging of 2 lists. So we use the look ahead to, because this is just an intersection of 2 lists. To increase the speed, we use some algorithms like look ahead and skip list, which is like you compare 2 pointers. In case you don't find a match, you do a skip list to skip to another list and you get the potential match. So at the end, you are left with all the potential matches for the inverted list. So for the next talk, I would like to call Professor Satoshi to continue.
So Kapil implemented most difficult part. I implemented easier part, the remaining part. So I quickly explain the filtering part. So he gave me candidate IDs, n-gram IDs, and what I have to do is find out the frequency or the ones. If, for example, if you ask AB, that's a bigram, and asking me the verb and location, and it is in the candidate, but there is no frequency on this pair. So we have to filter out these candidates. And how to do it? We have simple idea is we record all the information in the n-gram. That's expensive. We need large space. The number of instances is so large, but number of combination is actually not that large. So what I did is we present these combination as ID and use a table to map to get the real information. That's reduced the size to 100 gigabytes of index. But that's something I did. And the last part is just display. So n-gram will be displayed in the order, in the descending order of frequency. The trick is simple. N-gram ID is ordered by frequency, so it's quick. And such as sentences are searched using suffix array, just simple. And POS chunk any are displayed with sentence, keyword index, and n-gram display. And document ID or title of Wikipedia and possibly some features of document can be displayed too. Okay. And this is size of data. The Wikipedia text we have is dump of last year's July or something, which has 1.7 billion words, 200 million sentences, 2.4 billion articles. And number of Ngrams are like this, up to 7 gram. This is comparable to Google Ngram. And the index size is like that. So in total, it is 530 gigabytes. That's actually smaller than I expected. Okay. So future works. So we designed these extra information as separate from the other part, so we can easily add more information. So we can add something like parts, co-reference, relation, genre, discourse, etc. And because the size of index is so small, I can extend n of ngram, not just 7, maybe 10 or 12. Okay, and we have some idea about compressing index or dictionary. And actually creating index is very hard right now. It takes about 3 days with 96 gigabyte of machine. So we want to reduce this load. Okay, and as somebody asked, we want to implement union operation for tokens as well. Okay, and the big message is this is available. One is available at this site. I'm sorry, maybe some of you tried, and if you are using the guest wireless network, it doesn't work. It needs it is using special port rather than 80. So guest account doesn't work. I want you to, but, and we are hosting at NYU, but I hope, I don't know, JHU would like to host this demo. Yeah, I'd like to talk with you. Also, it's available here. Okay. So, how can I put this? So I want to show you that it works. Simply, so this is 2 terabyte disk. I prepare so that it can be bigger than that. So what I did is just plug in this USB here and make a directory, mount this disk, and change directory to there. That's it. And oops. And you just type, I love you, I love something. You just get it. Okay. Or I love NP. Oh. Missing. Oh. Okay. How can I? Okay. NP. Oops. Oh. I love NP. NP.
You have 2 stars.
Yeah, 2 star. 2 star means this is a beginning. This is information about chunk. 1 star means POS. 3 star means named entity. So that's how I encode it. So if you bring this back, maybe you can use from tonight. So that's okay. I can make auction here.
This contains only Wikipedia or Google?
This is Wikipedia only. Yeah, we made index for Wikipedia. Oh, we can easily make for Google too.
Okay, any questions?
Thank you.
So this is like a 2-page summary of the workshop. So what did we do? Well, essentially, we kind of developed techniques and experimented with unsupervised and semi-supervised learning techniques with the Ngram data. And we actually, like looking back, we applied quite a variety of techniques. One is to use observable proxies to estimate the probability of unobservable properties, like say gender, animacy, countability, and so on. They're not necessarily like observable from the straight text, but we can find like clues in like using pronouns or relative pronouns and so on to estimate those properties. And we also did something like which is kind of like global inference over the Ngram data, which not necessarily just looking at local context, but looking at sort of the related counts in different parts of the corpus. Like in the VBD, VBN example, we certainly want to do it more and do it more systematically and more sort of automatically. And we also did distributional clustering of the Ngrams, and finally we use the Ngram-based features in supervised training and improve the performance. And so this is in both like the VBD, VBN example and also the compound noun parsing. And I think kind of like this is the Ngram-based features. They are sort of independent of whatever like the supervised learning algorithm was kind of using, like in both parsing and part-of-speech tagging. Like so they are able to contribute sort of like independent evidence, and it's easier to make contributions, like further improvements. So so we made a bunch of promises, like when proposing the workshop, and thank you the sponsors for accepting it. So what do we do? Well, we developed a bunch of software tools. Here's a concrete example, and we have like demos and documentation for these tools that the community could use. And we also have created lexical resources that are like enriched Ngram dataset out of this workshop and distributional clusters and so on. And we have the state-of-the-art, like new state-of-the-art experimental results in a number of NLP tasks. And finally, kind of like the team, people kind of come to this workshop and go home with more ideas and momentum for further research. And so that's the summary. And finally, I want to thank Hopkins and the CLSP for hosting this workshop. And I want to thank Fred for running this whole series for over 15 years, and for Sanjeev for the overall like management for the workshop. And I also want to thank David Yaroski for being part of our team and provide like guidance, because actually one of the characteristics for our team is that other than David, none of us have ever been to a Hopkins workshop before, so we have no idea what's going on. Like I have to like ask me, what's it like? I don't even know the lab setup, so yeah. But with David, we certainly get a lot of insights. And I also want to thank Chris for loaning us the 12 terabyte disk that we have been using a lot. And at some time, like the disk was kept very, very busy. Like the load factor was like 15 for like a whole day or something like that. And I also want to thank Jason and Damiano for like participating in update meetings and interactions and so on. And I also want to thank the support staff at Hopkins, and we had a good experience here. And I also want to thank my sponsors at Google, or Thorsten Brand for helping with Ngram extraction, and my Fernando and Alfred for getting approval and for getting the funding for the workshop, and for the use for getting access to the Google IBM cluster.
Please thank them for us.
All right, I will. And finally, I want to thank all the participants, and this has been a good experience. And I certainly speak for myself, and from what I hear, and I'm speaking for the team as well. Thank you very much. All right.
There might be questions for the entire team, so
Okay.
are there any?
So if we want to start using your software and the documentation and read the documentation, where's the best place to start looking? Is there one place that aggregates all of these things?
Right now, there isn't one place yet. The different tools are in individual directories, but we do have the setup will be maintained for a while, and we're not doing it tomorrow because people are anxious to do something else to conferences and so on. So, but we will gather them together. Yes.
Will we have access to the Google Ngram data after the workshop team goes?
Yeah, the Hopkins lab has a license to use it. Yeah, and so is the so are for the participants.
So we have the license for everything you create here.
Yes.
Right.
Yes.
I was going to say an answer. It's further to Chris's question that perhaps Kailash, Sushant, and Kapil can take it as their task to put everything together.
All right.
Not just people at Hopkins, but people outside can have access to them. Because some of your tools I see are already on the web server, and we'll migrate Satoshi's tools here and then everything. So your team web page can become your portal to the rest of the world.
Yes. Yes, that will be nice.
Also, don't forget that you have to, that we would like you to insist on a report by October 15th.
Okay.
And it would be good if it had that report had directions on how to use the data and the facilities you worked out.
All right. Okay.
I had some silly questions, but I was trying Kailash's tool, and it looks like Lake Tahoe and Lake Victoria have a similarity of 0.43. And Lake Tahoe and Lake District have a similarity of 0.84. Lake Tahoe is more like the Lake District than it is like Lake Victoria. Can you figure why that happened?
That seems quite reasonable, actually, given the...
Lake District, that's also like a touristy kind of place, right? And where's
So is Lake Victoria?
Lake Victoria is which Lake Victoria?
Yeah, there's more than one.
Well, there are more than one touristy place. So I'm thinking about the one in Africa.
Yeah. Well, there's a bias on the web. There aren't much data about Africa, maybe.
We normally allocate the end to general discussion of what went on here in the three groups, or how the workshop was run, or actually questions to all three teams. I don't see Steve, but I do see Yeah.
Steve's over there.
Oh, Steve is there. Well, it was
Well,
true
that
that
did-
I didn't see him.
The statement's correct.
Yes.
So I've got a general question for the Ngram team, which is that you've motivated this approach as being one that can solve some of these really hard problems, and that would be like the disambiguations and other coordinations, things that historically we thought need really sophisticated representation and reasoning capabilities. So now that you've done more of these experiments, how optimistic are you with that original thesis? I mean, how general do you think these sorts of techniques could be?
Yeah, we the design for like how we do this is like to make it easy to integrate into like a full parser, for example. So so we have like a very simple program to use these scores from Emily's classifiers to create a parse tree for these just the noun phrases, right? But like if you have a full parser, you can take the log probability from Emily's parser as a feature in your parser to put them as part of the whole the score for a whole parse tree. And so it's like the like in Kalash's example, like we expect now like we generate like these similarities, even though for evaluation we have to make a decision, but like to integrate that into a bigger environment, you can use like these similarity scores as part of feature in your parser. So that's the.
But let me ask a slightly different question then. So if we take the parsing example, will there always be still really hard ambiguities for which we will need to do some sort of sophisticated representation and reasoning? Or could this solve all the problems eventually if we had enough data for these sorts of simple techniques?
Yeah, I mean, there will always be the last, I don't know, like a 3%. I mean, we'll be pretty happy to when it's like part of speech tagging, like when it's reduced to 3%, it's really hard to do like a new research on it, and people just assume it works. Yeah, but I think what we learned from like working with these Ngram is that you can do more than it appears to be. Like there are things that looks like it may require sort of world knowledge, but like if you have like these pretty superficial statistics, you can get like these probabilities, like I don't know, like gender, for example. Like I mean, to figure out so what is the probability? Like if you just know like say nurse, what's the probability of a nurse being male, female, neutral, and so on. Like it is kind of like world knowledge, right? But we with Ngrams we get like a probability distribution. Like we don't claim it is sort of exact like the world like distribution, but it is like a reasonable reflection of that.
Can I take a stab at that? I think it's a classic case of the glass being half full or half empty. You can do more with these methods than you might have thought, but there are definite limitations. Now that said, I think we had this talk where we were looking at 150 different problems, and it found there was no silver bullet. There were methods that worked better on this, and methods that worked better on that. One of the things I'm concerned about with sort of traditional standard parsing approaches is that we're sort of taking this view that long-distance dependencies are everything. We're trying to use the method that's appropriate for some problems, for problems that it doesn't particularly work well on. Right? Now, and a lot of the long-distance dependencies, it's not obvious, even for those, that you would do better by making the representation richer or by using context-free methods or something. So, I mean, I think what we got to do is to look at each of the different problems and try to come up with a hammer that's appropriate for that, and not to try to look for a single hammer that's going to do everything.
Yes.
I have a question for the parser team, maybe a silly question. But does the parser output any probability of the parse given the sentence? So if I have a sentence and parse is generated, say one best, can I get the goodness factor?
So the answer is no, but it would actually be very easy to do. So right now it doesn't spit out any probabilities, but getting that number out, it happens inside the parser. It just turns out we don't print it right now.
So if you have
Well,
access
that's about creating the super tags.
Yeah. So, well, okay, so if you had a probability with respect to the prune super tags, then yes, it's very easy.
So if you have access to the code, is it possible to get the probability or the score easily?
Yeah.
Okay, thanks.
While we edit, you left your you are leaving your parser here, are you?
We want to take it with us.
No. You can, no. This is the advantage of computers, that something can be on many places. But
Well, anyone can download the source code to the parser. And
that's
compile
my
it.
question,
So,
right?
Yeah.
and do you have you don't have a storage of parses, do you? Well, you said you're going to parse Wikipedia, etc. Is there a data set which has all these parse?
No, there will be. And that will also be on the same website.
Okay.
This is the website which has the CLC tools logo.
Yeah.
There's links off my webpage, right? So very easy.
Anybody?
So I have a question for the parsing team also. So what does power set mean?
That's a dangerous question.
We don't really know.
They were going to parse Wikipedia as their first step in parsing the web, if I remember.
Oh, rephrase the question. Maybe I misunderstood.
Yeah, that's what power set thinks of this work, or where you stand with I mean, they were going to do an LFG parse of the web, which is another.
Well, they have the LFG parser, of course, that is central to their technology.
Right. Have they used it to parse Wikipedia?
Yeah. So that's, as I understand it, that's what powers the whole search engine.
Yeah. Do we know anything about how those parsers would compare? Sorry, I don't. You had enough evaluation questions.
Well, so the person that we're in touch with said that, just informed me that they weren't that interested in the parser going faster, actually, which is quite interesting. I thought it was fast enough already, so they've got enough machines and so on. I don't know, I don't really have a sensible answer to that question.
Just curious.
Any questions for Dan, so he doesn't feel bad?
I think he answered some of the same kind of question yesterday about availability of tools. He said that we're going to make it available sometime soon.
Yeah.
That if somebody wanted the current version, that we like to have.
Well,
That's a
so
promise we hold you.
oh, there is a
Yeah, just kind of a general question. I know that the slides from yesterday morning's presentation were available. Are the other slides going to be available as well?
Yeah, shall we send it to Justin?
Yeah, just send it to Justin. We'll put a link on your page.
any other questions or comments?
Comments for the team, but others can.
I've got a similar question. All the videos that have been
Yes.
are they available? Will they be available?
Well, they will be available.
Yeah. We have to figure out a good way to put them somewhere on the web where it doesn't kill our server.
Right now, we're talking to videolectures.net about giving them a dump of 15 years of this stuff. I mean, working on some, old, release agreements and so forth. I don't know if we made you sign, if you guys signed anything for the videos here.
But also as a more immediate solution, our AV services, I think, can replicate the DVDs pretty inexpensively.
Actually, they have no big desk. They just have to give.
Yeah, or you can just get a physical DVD for $12.
Any other comments?
Well, I have a couple of comments for all the three teams. One is that in the past, several teams have managed to talk to some conference organizers, maybe NACL or ICASP or somebody, and get a sort of special session to talk about all the work that the team did. So I would say that you should try and explore that angle. And the thing is that if there are others who are not in the workshop or working on very similar things, for example, if the power set guys have something to contribute to a special session that your team might have, or if somebody else is doing things with Ngrams, then of course this can be an inclusive session. It doesn't have to be exclusive to you guys, but that has in the past been a very good venue to get this work out, better known to the rest of the world. So I would encourage you to look into that. And like I said, there's a history for this, so you won't be sort of asking for anything new. It has been done in the past.
Well, Steve's the ACL program chair.
Okay,
So
that's
we're in a good position to arrange that up.
or maybe a different position, I don't know. Yeah, that's one part. The other one is the report. Fred mentioned it already, but like, we'd like you to write up everything in a nice way, and that also becomes a very useful document. You often don't see it, but I get requests very often saying, oh, this final report link is broken, can you please fix it? So I know that there are lots of people out there in the world who download and read your final report. So, I mean, it kind of reads like a PhD thesis. It is a whole bunch of words very tightly written. There's no page limit for one, so you won't be forced to fit it into any number of pages. You can write as long as you like. So that's another important thing. And the third thing is that when you write papers and publish them and so on, please acknowledge the workshop. It's funded 50% roughly by NSF, 20% by DARPA, 20% by Google, and 10% by DoD. So you have many sponsors, and they all like to see. In fact, it's probably enough just to acknowledge the NSF grant and say the work done at GHU, because the other sponsors don't have a direct grant number to talk about, but the acknowledgement of the contribution.
So Sanjay, could you send out then to the teams, you've got
I'll
a
do
block
that.
of text?
Yeah, there's a little boilerplate. Yeah, there's NSF.
We should run it by the sponsors to make sure that they're acknowledged to their satisfaction.
Yeah, that's what they've asked for in the past. It's not that it's a new grant.
So for myself, no, go ahead.
Well, maybe you.
No,
maybe
no,
that's
no,
what
no,
you were
you
gonna say. I just
say-
wanted to say I really enjoyed the last day and a half. I think all three teams have done a super job of presenting work that is that's hung together and has really been interesting to listen to, and I think is going to inspire future work. It certainly got me thinking about stuff. I think this has been a great summer.
Let me amend that by saying I've enjoyed the last 6 weeks.
You took the words out of my mouth. In any case, I
That's the
think.
beauty of computers; they're still internet.
Right. I think this year's workshop, according to what I heard, was very successful and comparable to the best that we've had in these last 15 years. I was particularly happy that most of the presentations were done by students, and it's obvious that we've selected them cleverly, and we study the applications actually, and it takes us some time, and so we know them, and then we send them to the team leaders, and they make the final choice out of a short list, and I think the students again came through, and we are very proud of them. So I just want to remind you that there is a banquet, and the banquet starts at 6 o'clock with a lot of drinks. And at some later time you are called to sit around the table and are served. So thank you for coming, and we'll see each other once more at least tonight.